you.
Very curious.
Thank you, and thanks a lot to the organizers for the opportunity to speak here. I moved to industry recently, but it's still math research. It's not a pure math research, so there is a lot of numerical experiments, and the results don't need to be provably optimal. The results just need to be good enough for applications. So there will be some applications. There will be maybe some geometry and representation theory, but there will be very little differential geometry because that's very much work in progress, as is the rest of the stuff, but still this differential geometric part is the least developed so far. So this is the rough outline of the talk. I will explain the basic model for the wireless communication, and then I'll show you how the Grassmannians appeared there quite naturally, and I will present some results on the geometry of Grassmannians. Yeah. So this is a joint work with a group, with a set of people, which is decomposed geographically into Huawei and University of Cantabria. So these are my colleagues that work on this. But most of what I will say here will be really just common knowledge in this area of signal processing. So the basic model of wireless communication is down here, and let me just unpack it for you. The wireless communication happens through electromagnetic waves, and they have amplitude and phase. But however they are actually implemented in the hardware, in the end you will end up with two real numbers for each antenna. So it's natural to model the underlying hardware or real world with complex numbers. And the advancement in wireless technology, in cell phones, these higher data rates are actually allowed just because of the higher number of antennas that was put to products a few years ago for 4G and so on. So what we have here is the vector x as a transmitted symbol. It's a complex vector, and the dimension of the space corresponds to the number of the antennas that we use for transmission. In our cell phones we have different number of antennas, usually much less, and so we receive some other vector from some other vector space. And the relationship between these, the transmitted signal and the received signal, is just this affine function. This is the basic model, and the matrix that encodes how the signal changes is the so-called channel matrix, which captures the environment. So yeah, I won't draw any pictures, but just imagine that from some antenna to some other antenna, the signal is reflected or goes through a forest or is blocked by some building and so on. So these effects are somehow captured in this vector H. And then of course we have just the white Gaussian noises, as is usual in applications. So you just have some errors in measurement, or just the electromagnetic waves are affected by heat present in the system. So this is just modeled by the complex version of the normal distribution. This sigma is the power of the noise, and the signal to noise ratio is up to some normalization, just the norm of this vector x divided by sigma. How do we actually transmit data? It's very simple. You just the basic idea is very simple. You just take a finite set. We call it constellation or codebook, and you consider the signals only just from this finite set. So here you have example of 3 different finite sets which are used in practice, and these sets are the squares, and you just label the set with binary strings. So ideally you would like to have the set of the size 2 to some power, and you can also notice that, for example, the neighboring signals have very close binary labeling. Right? They usually differ just by 1 bit. This is quite important for applications, as you can imagine, all these questions like how to actually label our set, how to pick our set, and so on, lead to some NP-complete problems. So a lot of optimization and heuristics is needed. So this is our constellation, and when we receive some vector, we end up not exactly at what we were sent, but somewhere close, hopefully. How much close is determined by the noise, and so then there are some techniques how to actually calculate which point has the maximum likelihood that was sent. Right? It's a whole business. There are lots of people working on that, how to actually do it efficiently, because you want to do it every few milliseconds. Right? So for example, here we have 16 points, so calculating the likelihood of each of those 16 points is easy, but if you have, let's say, 128 points or 1024 points, then going through all these points will be infeasible, and there needs to be some kind of approximations. So that's one area that we work on. But let me explain maybe some parts which are directly related to geometry and mainly to homogeneous spaces, because usually you are on the move, right? And usually there can be several frequencies that you can send the data on. So the channel matrix is not really fixed. It changes in time, and it can be different for each frequency. So what we are really doing is we are looking at some two-dimensional submanifold of the matrices, and of course there are a lot of different models for this channel matrix, how it behaves. Some of them coming directly from the Maxwell equations, but the baseline is just model it as a random matrix. The simplest thing you can think of, just independently distributed random matrix, or maybe with some correlations. So these correlations are very important for applications because they allow you to suppress some interference, or they allow you to use the channel in better way. So how does it actually work in practice? Because when you turn on your mobile phone, you don't have the channel matrix, right? Where would you get it? So the communication protocol dictates that there will be some pilot signals which are known both to transmitter and the receiver. And if you know what you should be receiving, you can use that information to actually estimate the channel matrix and to estimate the correlation matrices that you would like to use for detection or improvement of the channel. And so the first problem is that when you keep adding antennas and when you keep increasing the bandwidth, these calculations became prohibitively expensive. Right? Estimating 2x2 matrix is easy. Estimating 16x16 matrix, it takes some time. And so what you would like to do is maybe to interpolate or maybe extrapolate in time, for example, this correlation matrix, right? Either in time domain or in frequency domain. But these correlation matrices are not arbitrary matrices, right? They are elements of this set, so they are Hermitian symmetric, they have positive eigenvalues, and they have ones on the diagonal. And so they live in this nice homogeneous space. But the question is, okay, we need to interpolate in this space, but what is the correct geometric structure here? Right? What is the correct distance here with which to actually calculate the interpolation? And in some situations, you can actually consider cases where you have the degenerate situations. So, for example, when you have some kind of occlusion, the signal is blocked by a building, then the correlation matrix is not of full rank, so you can then look at the boundaries of this space, and there is lots of interesting stuff happening. But I will move on to one of the projects that we have there in the Huawei, and that's the problem of beamforming or pre-coding. So the channel matrix is estimated at the receiver, but if the transmitter has some information about it, we can use it to improve the transmission. The idea is basically consider the singular value decomposition of H, and then send the signal just through directions corresponding to the largest singular values. Right? If the singular value is very small, it can be just drowned by the noise. And so you would like to let the transmitter know what are the singular vectors corresponding to the largest singular values. So let's say you fix 3 or 4 singular values, which are the largest, and you would like to send back the information which directions are good to the transmitter. And this precoding, there is linear precoding, non-linear precoding, whatever. Basically, you just, this symbol that you started with, you just change it somehow based on the singular vectors. And so the question is, okay, how do we efficiently send back these singular vectors? Because, and how can we keep track of them? Because again, it's something you don't want to do every 20 milliseconds. Right? So what is the space of singular vectors? So singular vector, even if it's normalized to have norm 1, is defined only up to phase. You can just multiply it with e to I of something, and it will still be a singular vector. So there is a natural U1 action, and the space of all possible singular vectors corresponding to k singular values. It's this one. It's just this nice homogeneous space. And if there are some degeneracies, in case we have some multiple singular values, we get this nice flat manifold. So the project has this following broad goal. We have this channel matrix that changes in time, and sometimes we have this observation of the actual singular vectors at that time. And this is called filtering, or the goal is to create a filter. Filter is a statistical device that has some underlying model, so you have some idea what the process should be like, what is the dynamics of the process. And then at some points in time you have measurements of the process, and the goal is to construct some update of the parameters of your dynamics so that you are as close to possible to actual state, you are as close to the actual state as possible. Yeah. So again, the question is, okay, we are on these nice homogeneous spaces. So what type of dynamics can we expect, or what type of dynamics can we efficiently work with? So right now we are just moving along geodesics. Then the question is, what is the good noise model for the observations? And then the question is, what is the optimal update of the parameters, basically how to choose optimally the direction of the geodesic and how far should we go along it. Yeah, so this is very much work in progress. We are being pushed. We have some problems with curvature because, of course, when you move in the Euclidean space and there is some error due to noise, and you move roughly in the same direction, you are not that far. But you can imagine that on a space with curvature, any like closed curve like this, like the real trajectory and the trajectory affected by noise, then this closed loop is affected by the curvature, right? By the what is it, Ambrose-Singer theorem. So that's one problem there. Another problem connected to this is actually how to send back the information which singular vectors do we measure at the receiver. And for that, the usual thing it would be just to take the manifold and decompose it into regions of roughly the same size, label the regions, and send back just the label, hey, we are in this region with our current singular vector. So we are looking at decomposition of this manifold into regions, and that's connected to the next problem, which is the problem of block fading, which starts somewhere else, but basically leads to the same question, but just for different manifold, this time for the Grassmannian. So assume that the channel matrix does not change for T transmissions, right? So let's say we are moving in a car in a street, so while we are like between the intersections, the buildings are roughly the same, the channel matrix doesn't change, but then we make a sharp left turn, and the channel matrix changes, but then again, before we reach the next intersection, it's roughly the same. So for T consecutive time periods, we have the same channel matrix, And so we can just stack these vectors together. So imagine that x1 up to xt are row vectors, right? So we have basically the same equation, but this time we are considering t by m matrices and t by n matrices. And we replace the norm of the vector x with the Frobenius norm of the matrix x. And the basic idea here in this situation is if we have no noise and we have the same number of antennas at the transmitter and the receiver, then the equation looks like this. So that's the noise model. And we see that y and x have the same space generated by its columns. Right? So if the number of antennas is smaller than the time, the t, the so-called coherence time, we can actually use this idea of column spaces of these matrices to send the information. So this is a picture of what's going on. I'm sending two matrices. These I can send one of two matrices. These are the blue rectangles, but I interpret these matrices as representatives of the subspaces, the black lines, right? And I get affected by noise. So this rectangle can be moved somewhere, but if the noise is not too big, if I receive something here, I'm pretty sure it was this line that was sent, not this one, right? So that's the basic idea. And you basically replace this vector space Cn with the Grassmannian Mt. And at the start, it's not clear whether this will be beneficial or not. I have to say that this idea is already 20 years old. Some people worked on it for some time, and then it kind of, there were no new papers, but with the addition of more and more antennas, people got interested in it again. So at the start, there is this obvious problem. When we are sending vectors, we have m times t degrees of freedom, and basically the dimension is m times t. But the Grassmannian has smaller dimensions, so it's not clear that it will be beneficial. But if you actually compare, if you just develop this idea, from start to finish and compare it, then you can see that there is a small or medium-sized win. So this bunch of lines is various variations on this idea of sending information through points on the Grassmannian. And this purple line is the pilot-based scheme, where we use half of the time, half of these T transmissions for sending the pilot signals, and the other half is used for sending the actual information. So this curve basically just shows you the performance. Here you have the signal-to-noise ratio, and here you have the error rate. So when we are using some crude approximation of the channel matrix, the error rate is actually higher than when we are not using it at all. So in this scenario, moving in car, there is some small benefit or medium benefit of using the Grassmannian for signaling. If you are sitting at a table in a cafe, then of course you can estimate age much more accurately, and then use this estimate for much longer time. So the clear winner would be this pilot-based scheme. So let me just show you the details of this Grassmannian signaling. So given some matrix T by M matrix X, when you assume that H is just this random matrix, this is the probability that you receive some specific Y, given that the send signal was X. So it's an easy enough formula to allow you to do some analysis. So first result here is that when you consider the constraint on power, you can actually show that the distribution on the signal that maximizes the mutual Shannon information is the uniform distribution of the Grassmannian. So you can just consider X being in the Stiefel manifold, just representing the points on the Grassmannian in natural way. And moreover, the formula allows you to actually calculate the pairwise error of mistaking two symbols. So it's not so nice. I mean, there is some integral, there is some product, but the upshot is that it's basically a rational function in the signal-to-noise ratio, and it depends only on these matrices only through this dm, which are the singular values of this product xi Hermitian conjugated times xj. So these singular values are the cosines of the principal angles between the subspaces. So you have very nice dependence on the actual geometry of the Grassmannian here. And you can do analysis for signal-to-noise ratio going to zero, so like a low SNR regime, where you can approximate this error by the so-called chordal distance of the Grassmannian. So here, these are the projectors on the subspace spanned by the columns of xi. This is the projectors spanned by the subspace of columns of xj. And this is the so-called chordal distance because it really corresponds in like a one-dimensional case to the chord on the sphere. And so you would like to minimize the probability of mistaking xi for xj. So you would like to maximize the minimal chordal distance here. High SNR limit gives you a very weird criterion where you have this determinant function, which is not a distance function. It's just something which is called coherence of subspaces in some literature. But for me, it's kind of mysterious. Why? Like, what does this determinant actually really means? And of course, you don't have to consider just maximum problems. You can just consider like the average or something like that. And it turns out actually that this union-bound criterion works the best. Okay, so you have some criterion how to actually find a constellation of points on the Grassmannian so that the error rate will be minimized. So how do you actually use it? So one idea is to really just go for numerical optimization. So here is the differential part of my talk. Finally, some gradient, right? So the idea is you just start with random constellation of points on the Grassmannian, and then you iteratively improve. So in each iteration, look at each point, and for each point you look at its closest neighbors, and you calculate the gradient of your cost function, and you try to improve in the direction where this cost function leads you. This works well. This produces very, very good constellations of points on Grassmannians. The problem is that it's quite computationally expensive. So let's say you want to create 128-point constellation, which means that you would have to optimize over a product of 128 Grassmannians. It's just quite big. Also for applications, you end up with basically random points in the Grassmannian which you need to store all of them and so on and so forth. So it has some downsides, but it gives you some benchmark. Another idea is the following. You basically want to somehow map lattice of points into the Grassmannian. You remember I showed you this lattice in the beginning. So you want to basically just map this kind of thing to the Grassmannian. So you can use your like previous knowledge how to label these sets and so on. So the idea is to take a unit hypercube and first map it to the complex vector space using the inverse of the distribution function. So from uniform distribution in the hypercube, we create a complex normal distribution, and then we have this nice map where we just multiply or rescale the vector with some factor, and I mean it's explicit, but it looks weird. But it was found just by demanding that from this complex normal distribution on the complex vector space, we want uniform distribution in the disk. And once we have uniform distribution in the disk, we can map to the Grassmannian using this easy map, and that's pretty much it. And all these maps are invertible. Okay, here in this second step, you have to do some root finding, but that's easy, right? That's one-dimensional problem. This is how it looks like. Here is just a lot of samples, and here is a lattice that we are actually using. So this is the first map from the uniform distribution to complex normal, from complex normal to uniform on the disk, and then from uniform on the disk to the Grassmannian. So here you are looking at the Hopf projection. And as you can see, there is some distortion here, so it's actually beneficial to not to shave off the points at the boundary. And of course, once you start shaving off points, you can say, okay, but we can actually use the other chart on CP1, right? So if you use the other chart, you will have some overlaps, but you can rotate the other chart by 45 degrees, and there will be no overlaps. So this is great. It works. But the question is how, like, what kind of rotation should one choose for higher T? Like when you have CP3 or CP4, it's not really clear how to rotate each chart so that the distance is controlled. The big question here is what can we do for higher Grassmannians? So this last map can be actually generalized. It's actually even simpler to morphism, so it's not just measure preserving, it preserves the syntactic forms which are there. But here, we instead of unit disk, we are looking at this ball in the operator norm of matrices, which is the Cartan symmetric domain of type 1. So the question is, how do we actually generate, or how do we map a hypercube into that? We don't know. So that's one open question here. Another different approach could be just to use the standard charts on the Grassmannian. We know what is the distribution. Like if you take uniform distribution of the Grassmannian, you obtain this probability density function on the chart. But again, we don't know how to put lattice points on this chart so that they are distributed in the limit in this way. So last, how much time do you have? Okay, so finally the last part, the representation field. So very natural idea, you have Grassmannian, it's a homogeneous space, so you just pick a finite subgroup and a base point, and you look at the orbit of the subgroup, right? So generically you will get an orbit that's as big as your group, but the base points actually matters a lot. So here you can see the histograms of the minimal pairwise distance for random base points. So you can see a lot of them are quite bad, but when you do some optimization, you improve quite a lot. So the question is, how do you actually pick a base point? So you start with some small examples, and you see that you can actually solve them analytically, and you see some square roots and so on. So you think, okay, maybe there is some idea how to do it, but then you go to the dihedral group D8, and the optimal base point is this guy. So, okay, you lose all hope, and you start again optimizing numerically. But right now, then you don't have to optimize over the product of Grassmannians. You are just optimizing one base point instead of calculating all possible pairs of distances and looking for the minimal one, because the distance function or the cost functions we are using are invariant. You have to calculate just the distance to the base point from arbitrary point, and you can do some further simplifications, and you obtain these problems for the base point. So the difference from the general cost functions is that now you have quartic dependence, you have degree 4 dependence on the base point. Before it was quadratic. Both criteria have this strange term there. Again, I don't know what it means, but it's clearly important for the result. And this is how it looks like. So I've implemented several series of finite groups, and there are some general bounds on the minimal distance, and this shows you what percentage of the bound I was able to attain. So these bounds are not sharp in general, and I was able to attain sometimes like 90%, but you see as the series goes, you attain less and less of the bound, and that's my last slide. That's because of this Jordan theorem. So these are the obstacles. So okay, the first one is not so serious. The classification is not done, so what? You can just go through the groups yourself and see what works. But then there is a very beautiful theorem by Alan Turing from 1938 that says that if you want to approximate the group by some other finite group in very like natural metric sense, approximate, then the only approximable groups are compact and abelian. So this is a bit discouraging. And then there is an even more classical theorem by Jordan, which basically bounds. It tells you the structure of finite subgroups. So there is a bound FD, which depends only on the dimension, which bounds the index of normal abelian subgroup of any finite subgroup of GLD. So I mean, you can convince yourself that when you have a abelian subgroup, it doesn't lead to good orbits in terms of these minimal distances. So this is basically this Jordan theorem is the phenomenon behind this behavior. But on the other hand, you can use big abelian subgroups for efficient decoding of the symbols. Okay, so thank you.